All right. Hi guys, my name is Japheth, and I'd like to share with you what I've learned about key value storage engines. If you have any questions, please put them in the comment, and then I'll get them. And also, if you've not liked and subscribed, please do the needful. Right. So let's get started. Um, so every database has a storage engine, and it's what allows the database to actually store data on the drive. So, but before we get to that, databases have several components. The first component is uh, query parsing and optimization. So what this does is when you write an SQL query or SQL query, depending on who was the English teacher, is that the database, the parser turns that into a query plan, and then the optimizer makes that query plan more efficient. Common optimization is called predicate pushdown. That is, you want to do the filters way earlier before you do things like joins, because then it reduces the amount of data that you have to work with. And then the other component is the query executor. What it does is simply just execute the query plan. And then there is the third component, which most of you must have or might have interacted with the most, is the index management. And an index essentially makes it easy to find your data in the database. Common approaches are using an LSM tree or a B plus tree. And LSM trees are better for write-heavy workloads because all writes happen in memory, in a mem table, and then it's moved to the disk. B plus tree have better read performance. A B plus tree is essentially it's like a binary tree, but instead of having instead of a node having two children, a node can have any number of children, more than two children. If we get time, we'll get into index management. If we don't, we can cover it some other time. And then finally, we have not finally, but we have the buffer manager. So the buffer manager essentially, what the buffer is a it's a write back cache. Essentially, it is a cache, and as you know, we can't use data unless it's in memory first, right? So the buffer manager manages that. How that works? How do we get data from disk? How we get the data in memory, and how the index and other components of the database then use the buffer manager to read and write data. Finally, the disk management component manages how we write to disk, making sure we write efficiently and effectively. So for this talk, we're going to cover three components: index management, buffer management, and disk management. I can promise to cover at least disk management and buffer management, and if we have time, index management. So disk management. So normally, most of us, if you've written a program, you've probably wrote a program that reads or writes to a file. Normally, you will write, say, some characters in the file, and then you'll either read the file line by line or character by character. So the disk manager does the same things. It reads and writes to files. Surprise, surprise. But what it does differently is it reads and writes chunks to the file. Normally, these chunks are 4 KB in size. They could be more. In some databases, the chunks are bigger. and we call these chunks pages. So we'll use pages from here onwards. And to know if the file, if we're reading line by line, we know where the second line is, right? But if you're reading chunk by chunk or page by page, to get the offset of where the page starts, you simply multiply the page ID, which is what we have here, with the chunks, with the page size. So this will give you 0, for example. So the first page starts at the 0th byte in the file, so on and so forth for the rest of the pages. So these are page ID. To get the position of the page in the file, you simply multiply the page ID to the page size. I mentioned earlier that the buffer pool manager is responsible for bringing data into memory. So this is how it does it. If the buffer wants to read a page of data from disk, what it does, it sends a disk request to the disk manager, telling it the page ID. If it's a write request, the disk request will have data, and the write flag will be set to true. And then the disk manager figures out what to do with the disk request, and then returns a response containing a success status and data for read requests. For write requests, it won't return any data; it just return or rather, the data field will be nil, and then the status will either be success or success or fail. So internally, the disk manager maintains a request queue. So for all requests that it receives, it puts them in a queue, and then it has a worker thread that reads requests from the queue and processes them. For example, in this case, the first the first request is a read request here. So the worker will pop the queue, get the read request, and then read the data, and then send the response to the buffer pool manager. Do the same for the write request, so on and so forth. But as you can see, or you might have guessed, this is very inefficient because the disk is internally parallel. That means it can have multiple threads writing to it at the same time. So we can increase the number of workers and have multiple workers reading from processing requests from the queue. The challenge with this approach is that we might have out of order, the request must be processed out of order because we have multiple workers, each just finding something from the queue and processing it. We might have requests for the same page. For example, in this case here, we see we should process read before write, and what ends up handling is that some requests end up being out of order. So having multiple workers reading from the same queue can be problematic, or rather will be problematic, because you can't determine the order. The order is not deterministic, the order in which requests are processed. So what we can do then in the disk manager is have multiple queues. We can have per page queues. That way, each worker is responsible for requests for a particular page. It sounds like wasteful, but whenever a queue is done, then there is cleanup that is going to happen, and then we can delete the queue, kill the worker to avoid leaks. So that was disk management. Next, we go to buffer management. And like I said, the buffer pool is essentially a cache. So after the buffer pool has made a request, what we saw here, after the buffer pool has made a request to say read a page of data, it then puts that data in a frame, in some frame. It has a bunch. Buffer pool maintains a number of frames. So that's what happens. Whenever there is a read request, gets the page from disk, puts it in the frame. If there is a write request, of course, it still has to fetch. If the page is not in memory, it still has to fetch the page. Sorry, if the page is not in disk, okay, so if the page is not in memory, it makes a request to read the page first before it can use it. And then the other component of the buffer pool manager is the page replacement policy. This is what determines what frame to evict or what page to evict from memory. And of course, during eviction, the page has to be written to disk. So that will result in a write disk request to the disk manager. So if the buffer pool, so if say we get the buffer pool manager gets a request to read a page, it first check, okay, is the page already in my is the page already in memory, or is the page cached? If it is, or if it's not, it checks if there is any free frame available. If there isn't, it evicts a frame, and then it can now use that frame to store data for a particular page. If the free frame is available, then it just reads the page, sends a read page disk request to the disk manager to read the page. So going deeper into the page replacement policy, a common scheme is the least recently used replacer. So this being the most recently used, like the newest, like the most recently used, and this one being the least recently used. So the LRU replacer, what it does is it evicts the oldest frame that was used, which sounds like it's enough, but it's prone to sequential flooding, whereby, say, assuming this is a list of pages, say for our index, we always want to have as much of the index pages in memory as we can, because we frequently read the index. But if we use an LRU replacement policy, what happens then is, if say if we do a table scan and we have to go through all the pages for a table, and say a page has five pages. So and assuming our buffer pool is full, then what is going to happen here is the buffer pool manager will say, okay, I'm full, so let me evict the least recently used page. So it will evict this page and then replace it with a new page, or evict it and update the data in that frame. Then we read the second page, so it has to evict this page as well, third, fourth, and fifth, so on and so forth. So essentially, after the table scan, we no longer have the index in memory, the index pages in memory. So the next query is going to be much slower, because then we'll have to refill sort of the index pages in memory again. An alternative is to use an LRUK replacement policy, where it not only considers the recency, but also the frequency of access for a page. So in this case, for example, we have a bunch of frames that have been accessed twice each, and then now we do the same thing. Like we do a table scan for a table with 5 pages again. So the first page will evict this frame here, but now when we're reading the second page for that table, our replacement policy will come and say, okay, this one is the least frequently accessed as this which will now be this one. This frame is the least frequently accessed. So it will reuse the same frame for the rest of the pages for that table. And after it's done with all the 5 pages, we still have a bunch of pages for a bunch of our index pages still in memory. So this is usually preferred to the bare bones LRU replacement policy. We have time for index management. So for the index management, I'm going to use this. I need to stop sharing and reshare again. Present, share screen. Right. So for index management, I'm going to explain the B+tree data structure using this tool. It's called btree.app. And I'm just going to add a few values. So we had 100, 101, 102, and 103. I'm assuming the V here stands for value. But essentially, it allows us to store keys and values. And what we have here, this rectangle here will be the equivalent, say, of a page. So now imagine if we had like, say, 100 items or 200 key value pairs. So this will be a page. So we'll first make a request to the buffer manager, tell it to, okay, please give me the root page for my B+tree. And then the buffer manager will figure out how to get that data in memory by making a disk request to the disk manager. And then the disk manager will respond with the data, and then we will add values to that root page. Now, when that root page becomes full, which is what I want to demonstrate here, by adding an extra item, you see there is a split, where there is a split, and then we have a new parent, a new root page. So this is very interesting because a binary tree grows top down, a B+tree grows bottom up. And as you can see, it's a lot more complex than this. It's even harder to implement one. But ideally is, now this here will create more pages. So for each node will be its own page on our storage. When you store it, will be its own page. And it stores key value pairs. And if you want to find say a number like say 100, the key with 100, it feels like more or less like binary search. If we come here, see, okay, yeah, it's less than 1 or 2, so you go to the left and then you get the value there. So in brief, that is what a B+tree is. And next week, I'll be going through, be doing a code walkthrough of the storage engine I built, which is called github.com. So yeah, next week around the same time, I will be going through the code walkthrough of how actually the code looks like for what I've just explained today. But I wanted to make this presentation short, so if there is any questions, I'll be happy to take them. I'm going to stop presenting now. I guess the page IDs have to map to a location on disk. Will a lookup table suffice? So a lookup table is stored in memory, right? So what happens when you turn off your computer then? But with that said, the buffer pool manager maintains a lookup table. So a page ID to page, I think it's page ID to page offset. I'm not sure. We'll see next week the lookup table on the buffer in the buffer pool manager. Yes. So essentially, all the pages are linked with each other, right? So you have the root page. So if you know the ID of the root page, you can get its offset, and then from that page, the root page, then you know where the children are, what the child pages are. So that works as well. Helps you find where the pages are. And also, all the leaf pages usually form a doubly linked list to allow you to scan, say, from a key to a particular key as well. In the example I showed from Bittree, they don't show the doubly linked list connections, but in the implementation that we'll see next week, we'll see that the leaf of the B plus tree is a former doubly linked list. Yeah, the root is, well, at least in my implementation, the root is predetermined. So I always know what the root page is. Um, right. I think you can give 1 more minute for questions. If there is none, then we can call it a day. All right. All right, guys. Thank you so much for your time. Have a good